that they're not dependent on one single administrative entity. So we tend to have a large number of these ASs on the top, and all of these ASs on the top will peer with each other. So these are ASs we call tier 1 ASs. They're the very top of the hierarchy. So what defines a tier 1 AS is it does not have a provider. And it peers with all other tier 1 ASs. Beyond that, there's a little bit of kind of informal notion of what makes you a tier 1 AS. Typically, if you look at the characteristics, these two things always hold. You don't have a provider, which means that you never pay anyone to carry traffic for you. And you peer with all the other tier 1 ASs. And sort of informally, if you look at them, they tend to be across at more than one continent. So you typically not have a tier 1 AS that is in only one continent. And they tend to own these kinds of transoceanic links that go, transatlantic links, trans-Pacific links. These are very expensive. They take care to manage. So the point at which you own and operate those links, you've kind of graduated to be a tier 1 AS. Examples, you'd probably heard of them. AT&T and Verizon are obviously the US ones we all know. In Europe, British Telecom, Deutsche Telekom. In Asia, Singtel, NTT. Those are some of the ASs that people would consider tier 1. Okay. This is kind of the context now that we've set up for inter-domain routing. Everything is going to be, we're going to talk about how we select paths and routes, is going to be in the context of this kind of setup, this ecosystem of ASs and business relationships. So any questions before I move on? Yeah? None necessarily. We use the term interchangeably. You can be an ISP without, okay, this is in the weeds of the details, so don't worry about it from an exam perspective, but you can be an ISP without being an autonomous system. So you could, for example, say that you're in a rural part of California where there is no connectivity. And so you're going to be an ISP in the sense that you go set up infrastructure and you provide connectivity to the people in that area. But actually, you just get a prefix from AT&T. You don't have your own autonomous system number. So that's a little bit just, differences in the practice. But the way we'll be using it, ISP and AS, you can think of them as equivalent. Yeah. Yeah. So all the tier 1 ASs will connect to each other in a full mesh, typically. Any other questions on this? Yeah? Yeah. That's the red link on top. Yeah. Yes, a lot. All the time. So as a tier 1 AS, certainly you would like it if these lower level ASs don't peer and they send all the traffic through you. They can't stop you from doing it. Right? Every AS acts independently in making those business relationships. So you can't block people from peering. Yeah. That's an interesting question. The question is, would you call someone like Google or an AWS a tier 1 AS? They have the footprint and the scale of a tier 1 AS, so they have the global networks, they have the transatlantic links. Typically, we don't because these cloud providers don't provide transit, meaning you go through Google's network if you're going to Google or from Google. But Google will not carry traffic typically to go between AWS and Azure, for example. And you can do it on top, but that's not a service they sell. So you can't sign up with Google the way you do with AT&T. And there's no technical reason they couldn't do it. It's just not the business they're in yet, at least. Any other questions? Okay. So where we're going to go from here now is if you have this ecosystem in your heads, we're going to start to design what that inter-domain routing should look like. Okay, and anytime we talk about we're going to design something, we have to start with what are our goals. Right? So what are the goals for inter-domain routing? In the context of intra-domain routing, we had these very clear goals. We said we want valid routes and we want least cost routes. Right? No loops, no dead ends, and least cost. In the context of inter-domain, we still want all of those things. We still want valid routes. You never want a route that loops. That's just not a good idea. But we have two additional goals. Any thoughts? Yeah? Okay, so stay within your system. I'm going to say that yes. Yep. Reduce cost. Anything else? Yeah, so that is the big one, though I'm going to call it what we call as policy. Okay, so the two goals, one is scalability, because now we are talking about routing at internet scale. Right? This is not routing within a single domain. We are literally talking about all the billions of hosts on the internet. That's the job of interdomain routing. But the second goal is, what all of you were getting at, which is what I'm going to call policy, but it's a slightly loosey-goosey term at this point. We'll make it more concrete a few slides from now. But think of it as meeting the business goals of the operator, which could be mostly to save money or to make money. Okay? So let's get to scaling, and I'm going to go through this a little fast because I think Murphy touched on it a fair bit. Yep. Question? We'll get to that. Hold that thought in just a minute. Well, you're absolutely right. Different countries will want to run their networks in their own way. I'm going to say that they want to have their own policies, and we'll talk about how they get to do that in just a few slides. Okay, so let's talk about scaling first. Right? What is the scaling challenge? It's simply that if I'm a router on the internet, give me any destination, and I have to know how to forward. I have to know how to find that next hop and send the packet on its way. Naive solution, we've talked about this. You could have an entry for every one of the 2 to the 32 IP addresses. Clearly, that would not scale, and Murphy went over this. And so Murphy, in his last lecture, said the key to scaling is how we do host addressing. And also said the way we do host addressing, if there's one word you should remember about IP addressing, it's hierarchical. It's hierarchical in the format, in the structure of the address. It's hierarchical in how we allocate the addresses. And finally, it's hierarchical. We're going to talk, Murphy's touched on those first 2 points. The last point is what I'm going to try and elaborate on today, which is how that hierarchy leads to routing scalability. Okay? So just a quick recap from Murphy's lecture. Remember, IP address is 32 bits. You can divide them into a network prefix and a host suffix. And the way allocation, or the way we hand out addresses, all the hosts in a network will share the same prefix. The important thing here is I can represent all the hosts in that network by just their prefix. And he also talked about how we have this dotted quad notation where I'm going to have something like a /23 to tell you what the prefix in this address is. For my convenience, in this lecture, I'm going to use a.b/16 rather than trying to read out numbers. Otherwise, I always read them out wrong. But this is, again, the structure, the hierarchical structure of an IP address. Any questions on this? Okay, great. So what is key for interdomain routing is you have to realize that destinations in interdomain routing, they are now prefixes. Right? So in all the routing we've talked about so far, distance vector, link state, a destination was the host address, the full host address. In interdomain routing, our destination is going to be a prefix, which represents all the hosts in that network. Okay, and why does this lead to scalability? It should be pretty clear. If you look at a topology like this, and we said LBL had a /16, x.y, and UCB had a /16 of p.q, and they're both customers of AT&T. Well, if you go look at a routing table in Verizon's network, it just has to have 2 entries, one for each prefix. Okay? This is already a massive improvement. We've basically aggregated all of those hosts. You could have had 2 to the 16 hosts in LBL and 2 to the 16 in UCB. Instead of enumerating all of them, I just have to store 2 prefixes. Okay, this also tells you how interdomain routing, how we're making this scale. The prefix is going to get you to the final domain, to Berkeley or to LBL. And then only within that domain, you're going to worry about getting to the exact host. Right? Is this make sense to everyone? Okay. The second aspect of why hierarchical addressing helps is that the allocation is hierarchical. Again, Murphy had this slide where he said address assignment, you get from ICANN, gives out prefixes to regional registries that give it out to organizations like AT&T that then you keep subdividing your prefix space as you allocate it. Okay. Look familiar? Why does this help me? Going back to the example we had, here I could have said, Well, AT&T could have said, LBL and Berkeley are both my customers. Instead of giving them these completely disjoint prefixes, I have this address space that's /8, A dot something. I'm going to go and hand out A dot B to LBL, and Berkeley gets an A dot C. And so what happens to Verizon's table, it now just has to store one entry that says, if you're A dot anything, just go to AT&T. Okay. So there's two slightly different forms of aggregation that have happened. The first one was just saying I'm aggregating all the host addresses into one prefix. And now I'm saying I'm going to actually aggregate prefixes into shorter prefixes. Okay? And so we're getting kind of this benefit from exploiting hierarchical addressing. There's another benefit to hierarchical allocation and addressing. So let's say I had UCSF came along and is given the prefix A dot D. What changes at Verizon? Does anything change? No. Right? It's a local change within AT&T's network. Verizon doesn't even need to know about it. So you get all this, yet another level of scalability. You don't send updates when you don't need to. So we like hierarchical allocation because of that. Hierarchical allocation addressing enables aggregation. Okay? So learn that lesson in your head. It's not perfect, though, and the reason it isn't is because ultimately, in order to get aggregation, hierarchy in addresses has to match the hierarchy in the topology. Okay? What do I mean by that? Let's go back to this picture here. And we've done beautiful hierarchical allocation and hierarchical addressing in this example. It matched the topology we had. Now let's say that LBL feels like they don't want to be dependent on just one provider. They really can't afford any kind of outage. So they say, I'm also going to sign up with Verizon as my provider. So I'm going to have two providers. This is something we call multi-homing. It happens all the time. Any AS or enterprise that is very sensitive to having outages might multi-home. They will go to multiple providers and say, I'm signing up with both of you for connectivity. What happens to Verizon's forwarding table in this case? Yeah. If I did nothing, I would just send my traffic to AT&T, which means my red link is going unused, which never makes sense, right? LBL paid for that link. They want it used. What would Verizon have to do? They would have to change their forwarding entries to make this work. Yeah, exactly. You would have to add yet another entry that says if you're going specifically to A dot B, then you need to go with this red link. Anything else that has the prefix A, you go to AT&T. And when we talk about IP routers, we're going to talk about how we implement this prefix matching. We call it longest prefix matching to decide which of the two links you should go out on. Okay? So, but the thing to note here is that when we do multi-homing, it limits the efficiency of aggregation. And that's because we're breaking this assumption that hierarchical address allocation maps onto a topology. Right, so IP addressing and why we get scalability, aggregation is what gives us routing scalability. But at the same time, the problem is aggregation can be broken by multi-homing. Okay, where multi-homing again means you've connected to more than one provider. And so where we end up at typically is kind of just how the two factors play out. So on the internet, you will see some providers that worry a lot about multi-homing making their tables larger. In certain parts of the network, there isn't much multi-homing, so you get very nice aggregation and scalability. But there's no solution, per se, to multi-homing. It exists, and it causes us some scaling challenges. In here? Yeah, great question. Should we have given LBL two different prefixes? We could have, right? That's your question. And you advertise one prefix to Verizon, another one to AT&T. You totally could. You're losing something there. What is it? The thing you're losing is that for any given address, you don't have the redundancy then. So let's say LBL had A dot B and also had P dot Q. If I now have a server that was given the IP address A dot B dot something, if AT&T goes down, you can't reach that server. even though I have Verizon as a provider. You could then do tricks later on to say, I'm going to give this